Assalamu alaikum everyone. So today we will be having our 13th lecture, right? So we will be solving different problems regarding the topics which we have studied so far, right? So one point I would like to mention over here, that those problems, they are taken from your textbook written by Mano, right? So let's start straight away. The first problem is that we have to obtain simplified Boolean expression, right, for this circuit, right? So we have 4 inputs, 2 outputs, right? So you will be computing F yourself. This is your homework, right? And I will be focusing on G. So if you look at G, right, and you can also realize that we have different terms at the output of each gate. So here if you look at this gate, right, so we have BC, right, and that BC is fetched here at the input of this OR gate, and we have the A complement. So we are having BC plus A complement as the output of this OR gate. Then we have this NAND gate, right? So this is A complement, then D and whole complement, right? So if I have to solve this, right, using, right, so what I can do, A complement, right, and then D, and then I have to mark the whole complement. So what we normally do, we break the line and change the signs. So A double complement plus D complement. So this double complement will cancel, right? So we are left with A D bar, right? So this is A D bar. So if you look here, right, so what we have BC, right, plus A bar, right? So if you have to compute, right, BC plus A complement, right, so we will be having A BC, right, plus A bar, right, plus B C D bar, right, and A bar D bar, right? So this will be cancelled out, right, because A dot A bar is equal to 0. So we are left with A B C plus B C D bar plus A bar D bar, right? So here you can see that we have ABC. So what is missing? D plus D bar, right? And if you look here, we have B C D bar, right, which is missing A, so A plus A bar. So that is equal to 1. This is also 1. And over here, right, we are missing B, right, and then we are missing C, right? So we are using very straightforward ABC D bar, right, plus A bar B C D bar, right? So I'm leaving this, right, because this can also be solved like this, right? So here you can see that we have 2 terms, they are the same terms, right? So you can see we have A B C D plus A B C D bar plus A bar B C D bar, right? So if I have to solve this and plot this, you will see that a lot of terms, they will be cancelled out or they will be eliminated in this way. Like we have the same terms, we have, right, we can include or we can use the Boolean algebra in order to have minimization, right? So if I have to plot, for example, ABC, right, D, right, so you can see that A, B, C, D, 1, right, A, B, C, D bar, right. If I move here, A, B, C, D bar, so here we have this, right, and similarly we have A bar, B, C, D bar, right, A bar, B, A bar, B, C, D bar, right, A bar, B, C, D bar. So here 1, and we will be having this 1, and then so overall we will be having M0, right, M2, M4, M6, M14 and M15. Now we will be looking for the groupings, right. So you can see that if I bend it vertically, right, so I will be having this square, right, these two ones and these two ones, right. So then after that I will be having this pair, right. So we will be having what, right, B will be cancelled out, so we are left with A bar, right, and here what we will be having, we will be having D bar, right. So A bar, D bar as a result of this square, and then as a result of this pair we will be having a term with 3 literals, right, because after the pair we normally get a term with 3 literals. So you can see that A, B, right, so D will be eliminated and we are left with C, right, so ABC. So this is the solution, and you can solve for F by yourself, right. Okay, so let's have another problem, right. So we have to design a combinational circuit, right, with 3 input and 1 output, right. So you have to draw, or you have to think about the variables. So we have named them X, Y, Z, and this is the output which is represented by F, right. So now the output is 1 when binary value of the inputs is less than 3, right. The output is 0 otherwise, right. So this is the problem, right. We have to design a combinational circuit. So you can see the output is 1 when binary value of the input is less than 3. So if I have to write down the decimal equivalent, right, so what I can do, so here I can have 0, right, 1, 2, 3, 4, 5, 6 and 7, right. So whenever the input is less than 3, right, the output is high, right. So you can see that we have 1, 1, 1, but after 3 we have 0, right. So we will be solving this. So you can see that we have used K-map in order to have simplification, right. So here we know that we have to decide, so this is X and this is Y, Z, so 0, 1, X bar X, right, Y bar Z bar, and Y bar Z, Y Z and Y Z bar. So M0, M1, right, so we jump from this column to the last column straight away, M2, M3, right. So here we have M4, M5, M6, M7. So you can see that this is M0, 1, M1, 1, right, M2, 1. So we will be having, if we bend, right, vertically, so we will be having this pair, right, this one M0 with M2, right, and then we can reuse this one, so we can reuse this one with this and we have another pair, right. So we will be having, as a result of this pair, after the bending we will be having S bar, right, and so here you can see that y bar will be eliminated and we are left with z bar, right? So if we talk about this pair, so here you can see that z bar is eliminated and we are left with x bar, y bar, right? So this is the f if we have this statement, right? So then there is another part, right? B, the output is 1 when binary value of the inputs is an odd number, right? So let's move to the other part of the problem, right? So you can see that the output is 1 whenever we have an odd input number, right? So if you look here, we have a 0, right? If I have to write down, we have the 0, right? This is 1, this is 2, right? This is 3, this is 4, 5, 6 and 7. So here we have the odd, this is also odd, right? This is also odd, this is also odd, right? So we have 1, 2, 3, 4 odd values, right? So I have to map them onto the K map. So we have x, y, z bar, right? So here you know M1, right? Then M3, this is M3, right? Then M5, this is M5 and this is M7. So we will be having straight away a square, right? So this square will give us only z, right? So x and x bar will be cancelled and y bar will also be cancelled, so we are left with z. So this is the solution to the second part, right? So let's move to another problem. We have to design a combinational circuits with 3 inputs, right? X, y and z, and 3 output, right? A, B, C. When the binary input is 0, 1, 2 or 3, the binary output is 2 greater than the input, right? So we have to be very, very careful, right? So this is 0, so we have to add, right? So the binary output is 2 greater than. So if I have a 0, 0 over here, right? Right? So this is 0, so this is what? 2. So this is, so you can see that in front of 0 we have this value, right? Right? Because the output is 2 greater than the input. So input is 0, 0, so if you have to make it 2 greater than, so we have to add a 2, binary 2, right? So if I take the final value, right? So I have to add 1, right? 0, 1 carry, 0, okay, because we have to, when the input is 0, 1, 2 or 3, right? So this is not the case, right? So we have to be careful. So let's talk about 3. So I have 0, 1, 1, 3, right? So if I have 0, 1, 2, 3, the input is 2 greater than the output is 2 greater than the input, right? So we have 1, 0, so 1, 0, so 1, 0, 1. So in front of 0, 1, 1, I will be having 1, 0, 1, right? 0, 1, 1. So, and the scenario changed when the binary input is 4, 5, 6 or 7, the binary output is 3 less than the input, right? So here I have to subtract, right? So if I have for example 1, 1, 1, right? So what is 3? So 0, 1, 1, this is 3. So I have to take the difference, 0, 0, 1. So this is the difference. So when the binary input is 4, 5, 6 or 7, right? Right? The binary output is 3 less than the input, right? So we have 3 inputs, 3 output. So straight away we will be implementing that truth table onto the K map, right? So you can see if we talk about A, right? So we have this, right? M0, M1, M2. So we have M2, then we have M3, right? And then we have M7, right? So we have two pairs, right? X bar, Y bar, and YZ, right? So this is for A. Now let's move to the B, right? For B, we have M0, M1, and this is M5, M6, right? M1, right? M0, M1, right? And then we have M5 and M6, right? So we have this pair, right? And this pair, and then we have this one, single one, right? So as a result of this single one, we will be having 3 literal term, right? And as a result of those pairs, we have 2 literal terms, right? This is X bar, Y bar, Z, right? So we will be left with this circuitry regarding B. So now talk about C. So if you look at C, we have M1, right? And then this is M3, right? And then we have M4 and M6, right? So you can see that we have this pair. If I bend them or twist them vertically, right, I will be having M4 and M6 as a pair, right? So you can see that we have the XOR functionality, X bar Z plus X Z bar, right? So this is the solution of the problem. So let's move to the 7-segment decoder, right? We have a 7-segment decoder, right? And let me straight away read out the statement that converts a decimal digit to BCD, right? Right? So we have different segments A, B, C, D, E, F, G, right? And we have to display different numbers. So if you look at the truth table, right? So this is the binary equivalent, right? Right? So if we have to display 0, we need A, B, C, D, E, F. A, B, C, D, E, F. And there is no G, 0, right? If we have to display 1, right? So the decimal 1, right? So we will be having 0, 0, 0, 1 because we need 4 bits in order to represent those decimal values, right? So we will be having B and C, right? So B and C is on, right? So if you look at this is decimal 9. So if you look at the 9, so 9 is like that, right? So we will be having A, B, C, D, right? So we have only A that is turned off. All other has to be turned on, right? So if we start from A, right? So we have M0, right? This is M2, right? M3, right? And then we have M5, M6, M7, right? And then we have M8 and M9, right? So this is A, and after the simplification we will be having this, right? And if you look at B, right? Remember that in one of our previous lectures we use don't care conditions in order to have simplification, right? So here we are not using the don't care conditions, right? So here we regarding B, so you can see that we have 0, M0, right? 1, right? And then this is 2, 3, 4, and then we have 7, right? And then 8 and 9, right? So here you can see that we have 8 and 9. So we will be having this, right? Whole row, right? And then this pair and this pair, right? Okay, so after simplification we will be having the expression for B is, right? And then if you look at C, right? So we have M0, M1, M0, M1, right? And then we have M3, right? This is M3, right? And then we have M4, M5, M6, M7, M8 and M9. So you can see M4, right, M5, M6, M7, M8 and M9, right. So we have a row, then we have this gear, then if I twist or I bend horizontally, I have this pair, and then we have M8 and M9 as another pair. So we are left with A bar B, A bar D, right, and then we have B bar, C bar, D bar, right. So we have two pairs. As a result of those two pairs, we have three literals, right, and we have one square, right, and here again we have another square, so we have two literals each for those four groupings, right. And then if you consider D, right, so you can see that we have M0, right, and we have M2, right, M2, right, and then we have M3, right, M5, M6, M8, M9, right. So here you can see that we have this pair, then this pair, then if I bend them horizontally, I will be having M0 and M8 as a pair, and this is the single one, right. So as a result of this single one, I will be having A bar B, C bar D, right. If you look here, we have A bar B and C bar D, right. So as a result of other three pairs, I will be having 1, 2, 3, 4, right. So we have four pairs, 1, 2, 3 and 4, four pairs. I will be having three literal terms, right, against those four pairs, right. So this is D, and if I move to E, so you can see M0, right, M2, right, and then we have M6, right, and then we have M8, right. So we are having two pairs. One is the straight pair, and other pair I got after bending. So M0 is paired with M8 after the bending or twisting, right. And then if you talk about F, right, so we have 1, right, M0, right, then we have M4, right, M5, M6, right, and then finally we have M8 and M9. So here you can see that we have this pair, and if I flip, right, I will be having M4 paired with M6, right, M8 and M9, right. So I will be having 1, 2, 3, 4 pairs. So you can see that we have 1, 2, 3, 4 terms, right. And finally we have to map G, right. So you can see that M3, M2, M3, right, M2, M3, right, M4, M5, right, and then M8 and M9, M8 and M9, right. So we are having this pair, right, and then this pair, and this one is reutilized or reused with this pairs, right. So we have 1, 2, 3, 4 different pairs. So we are having 4 terms, each term having 3 literals, right. So this is the solution for BCD to 7 segment display, right. So here we have another problem, right. We have to design a combinational circuit that converts a 4-bit gray code to 4-bit binary number, right. So this is the gray code, right, and this is the decimal equivalent, and here again this is the gray code, and this is the binary equivalent. So you can see we have labeled the gray code as an input having variables A, B, C, D, right, and then we have labeled the converted binary as W, X, Y, Z, right. So what we will be having this as an input, and this is the output. So we will be solving them one by one. So if you look at the W, right, so if this is the 0, 0, right, this is the gray code, right, and this is the binary equivalent. Again, this is the gray code, so we have 2. This is the gray code, we have 3, right, 4, right, 4, and this is the gray code, that corresponds to this 4, right? So this is 5, and equivalent gray code 6, right? Equivalent gray code, and so forth. So we will be having W, X, Y, Z, right, as output, and we have to compute this individual variable representing the output in terms of A, B, C, D, right? So here, if I have to focus on W, so you can see that 0, 1, 2, 3, 4, 5, 6, 7. After 8, I have all ones, right? So you can see that 8, 9, 10, 11, 12, 13, 14, 15. So I have a quad. So as a result of this quad, I have only A, right? So then I will be focusing on X, right? So if you look at X, right, so here we have M4, M5, right, M6, M7, right, and then we have 8, 9, 10, right, 11, right? So we have rest of the bits high, right? So you can see that we have this grouping, right, in a row, right, and then we are this grouping again at the bottom row. So we are left with A bar B, A bar B, and AB bar, right? So this is the XOR operation, right? So if you, this is for X. Now we have to focus on Y, right? So in Y you can see that this is 0, 1, 2, and then 3, 2, 3, right? And then we are having 4 and 5, right? This is 4 and 5, right? And then we have 8 and 9, right? And then finally we have 14 and 15, right? So you can pair them, right? So this is, as a result of this pair, we will be getting right, A bar, B bar, right? And what is eliminated, D is eliminated, A bar, B bar, C, right? And then AB, right, as if you look at this pair, so here we have A bar B, D will be eliminated, we are left with C bar, right? So here we have AB bar, right, AB bar, if you look at this pair, right, and we are left with C because D is eliminated over here. So if you look at here, AB, and then we have C because D is eliminated again. So if we pair them, right, you can take A bar as common, so B bar C, B C bar, so you can have right, B, right, so B bar, B XORed with C, right? So here A XORed with B, right? So after the simplification we are left with this, right? So we can take A XORed with B as X, right? So this is the simplification, right? So this is for Y. Now move to the Z, right? For Z you can see we have, right, so we have adjacent pairs, so we can use McCluskey method over here. So after the simplification we are left with A XORed with B XORed with C XORed with D. So these, right, you can see, or you can map this as, right, so we can have A, B, C, D, right? So A XOR B, right? So we are left with a single, right, XOR gate, right, with 4 inputs. Okay, so this is the solution to the problem. So now let's move to the another problem. So we have to design a circuit that is called ones detector, right? So what the problem is that we have to detect the number of consecutive ones, right? So here what we will be having, right? So let's we have 8 different bits, right, or 8 different. So here if I have 8 slots, right, 3 and this is 4, this is 5, right, 1 2 3 4 5 6 7 8, right? So how I can have, so I've named them A, B, C, D, E, F, G, H, right? So I have a scenario over here. Here I have consecutive, right, ones, right, 3 consecutive ones. So the second scenario can be, here I can also have 3 consecutive ones, right? So here I have consecutive ones, right, and here I have consecutive ones, and here I have consecutive ones, right? So here I have consecutive ones. So this is the possible number of combinations where we can have 3 consecutive ones, right? So how I will be, so because they all are possible, so this one or 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 this one, right? So what I have to do, so all consecutive ones, how I can do that? So here I will be having A, B, C, right, B, C, D, right, C, D, E, right, D, E, F, right, E, F, G, right, F, G, H. So this is the logic, right? So let's, so imagine if we start solving this problem via truth table, right? So how many variables we have? We have 8 variables, right? So how many combinations or unique combinations we have? 2 raised to power 8. So you have to test 256 rows, and that is not an easy task, right? So what we did over here, we have think logically and we have reached the solution. So I made slots, different slots, right? And you can see that how there are different possibilities how we can have 3 consecutive ones, right? So you can see that we have all the possibilities and then we have ORed them. So this or this or this or this and so on and so forth. So I have ABC plus BCD, CDE plus DEF plus EFGH plus FGH, right? Now, so we have to implement the function. So this is the function, right? So you can see we have ABC AND gate, 3 inputs, BCD AND gate with 3 inputs, CDE AND gate with 3 inputs, right? Then we have DEF AND gate with 3 inputs, EFGH, FGH. So this or this, right, or this or this or this or this, right? So here you can see we need an OR operation, so this is the required solution, right? Then here is another example that we have to count the number of ones, right? So if we have 3 variables, right, so A, B, C, so these are the number of ones. So here we have 0, 1, 1, right, 1, we have only 1, right? So 2 ones, right, 1, 2 ones, this A and C are ones, then A and B are ones, and here we have 3 ones, right? So we have to count the number of ones. So if I have to represent, because I am dealing with binary, right, number system, or I have to design a digital circuit that is based on binary, right? So I have to represent those numbers in binary. So 0, 1, 0, 1, 1, 0, 1, 2, right? 1, 0, right? 0, 1, so 3, 1, 1, right? So if you write down the corresponding decimal, so you can see that this is 3, right? So now I have to focus on different outputs and I have to draw the circuit. So here you can see that we have, right? If you draw the if you have to compute the equation, right? So here you can see that we have this one, right? So here we have A bar B C, right? And then here we have A B bar C, A B bar C, and finally this is the second last term, A B C bar A B C, right? So this is for Y, right? And then we have to compute Z, right? So A bar B bar C, A bar B bar C, A bar B C bar, right? A bar B C bar. Here we have A B bar C bar, A B bar C bar, and then we have A B C, right? And then we have to implement the circuitry, right? So you can see that we have Y, right? So A B C ended, right? A B C ended. So this is A bar, this is B bar. We have handled the complement externally, right? So this is AB, right? Right. So here, so this is for Y. So here we have A bar B C, right? A bar B C, right? Here A B bar C, A B C bar, right? So if I take common, right, from here A B, so I will left with C into C bar, right? Right. So if I write here, so AB common, right? C plus C bar, right? So this is 1. So that's why we have AB, right, ended, and this is then all have to be ORed, added, right? So if you look at Z, so you can see that A bar B bar, they are complemented. We have controlled the complements externally, right? And then we have C, they are ended, right? And then A bar B C bar, right? A bar B C bar, right? And then A B bar C bar, A B bar C bar, and A B C, right? So here we don't have any sort of simplification like here, right? So here we have eliminated one literal, right? C, that is C bar from here and C from here, one literal from each term, right? And we are left with a term with two literals, right? And you can see that this is our Z, right? So today's lecture we have tried to design some of the digital circuits, right, on the basis of the required functionality, right? So like if you look here, we have a circuit that can detect 3 consecutive ones, right? Here we have designed a circuit that is counting the number of ones, right? So if you go back, right, so we have different functionalities and we have designed the circuitry for those different functionalities, right, by using our analysis and design experience and exposure. So that's all for today's lecture. So मेरी तरफ से आप सबको अल्लाह हाफ़िज़, अस्सलाम वालेकुम।